Hello everyone, welcome to our course on machine learning for beginners. My name is Brendan and I will be your instructor for this course. We have prepared an awesome lesson plan which will help you get started with machine learning in no time at all. You will learn all about different types of machine learning algorithms and in several cases, we'll implement them on live coding projects. You will learn about supervised learning, unsupervised learning, neural networks, and real-world machine learning. There will be quizzes at the end of each unit to reinforce your understanding of the concepts discussed in the lectures. Furthermore, there will be many projects where we will explore real-world machine learning implementation. In order to complete this course, you must have some basic programming knowledge in Python, since we will use Python for the projects. Furthermore, a mathematical background will help you understand the algorithms, but it isn't entirely necessary. I am very excited to teach you all about machine learning in our beginners course, so let's get started.
Hello everybody, welcome to this course, Machine Learning for Absolute Beginners, an introductory course by Edionics. My name is Brendan Crabb. I'm going to be with you for the entirety of this course, and I can't wait to teach you guys a little bit about one of my passions, and that is machine learning. So let's go ahead and get started and dive right in. Unit 1, we're just going to cover a broad introduction to machine learning. So this is going to be a 4-video series if all goes according to plan. The first being this one, just what is machine learning? Hopefully we can answer this question by the end of this presentation. Video 2 is going to be on the types and applications of machine learning. So in this video we're going to dive into actual use case examples of machine learning in today's society and cover all the different types of algorithms that there are and how they're being used. Number 3, we're going to address artificial intelligence versus machine learning. There's a lot of misconceptions in this area that I think should be addressed early on. So we're going to understand a little bit more about AI and how it differs from machine learning and where it overlaps. Number 4, we're going to talk about the essential mathematics for machine learning and AI. There are several core competencies that you're going to have to know going in if you want to get the most out of machine learning. And so those include topics like linear algebra and multivariate calculus, but we will cover that more in depth in the fourth video. So let's get started. Let's talk about machine learning. So what is machine learning? This is the question that this video is going to cover. Let's try to address that now. So I want to start with this comic that I think does a good job of portraying the current state of understanding of machine learning. So this is the Dilbert Daily strip by Scott Adams. And in this strip, we have an individual who is interacting with a computer, doesn't know quite what it's doing, and as a result, the term machine learning is applied to it. There's plenty of sci-fi movies out there that have claimed that AI and machine learning algorithms are going to try to kill us. But that isn't actually the case, so let's hopefully clear up some of those misconceptions so that we don't have to just use the buzzword machine learning whenever we don't understand what our computer is doing. So what we lack in knowledge, we make up for in data. And this is at the core of what machine learning is. So machine learning is simply inferring knowledge from data. And then the learning step is when we're optimizing a performance criterion. So the machine learning is simply programming computers to optimize a performance criterion using example data or past experience. We have a model defined up to some parameters, and learning is going to be the execution of a computer program to optimize the parameters of the model using the training data or past experience. So that's the gist of it. At the core, it is inferring knowledge from data, gathering knowledge from data, however you want to say it, and then optimizing the parameters so that we can get better and better at whatever we are trying to do. So let's keep going. There are a couple main types of machine learning models that can be differentiated. So the first is predictive. About half the models are going to be predictive in that they are trying to make predictions on the future. So an example of this might be to predict whether a patient hospitalized due to a heart attack will have a second heart attack. So that would be an application in the healthcare field. The prediction in this case would be based on demographic, diet, and clinical measurements for that patient. Another example might be to predict the price of a stock in 6 months from now. We'd all like to do that. That could make quite a bit of money. And we would do that on the basis of company performance measures and other economic data. Another example would be to maybe estimate the amount of glucose in the blood of a diabetic person from an infrared absorption spectrum of that person's blood. And that would be another very beneficial use case scenario in the healthcare field. So the second class of machine learning models that we'll talk about are descriptive models. And these are simply trying to gain knowledge from data. And so this sounds more like our general definition of machine learning that we just gave in the previous slide. However, in descriptive models, the difference is that we're not going to have an expected output necessarily. So we only have input data to give it, and we're going to try to gather knowledge from that data. So an example of this would be basket analysis, such as learning associations. So in a supermarket, you could try to find associations between products bought by customers in that market, because that would be very valuable for the store to know, because then they could advertise and market towards those customers more effectively. Another one would be to potentially identify the risk factors for prostate cancer based on clinical and demographic variables. So we don't necessarily know what the output's going to look like, but we're going to try to gather that knowledge by analyzing this data. Okay, so these two types of learning can really be broken down into supervised learning and unsupervised learning. Again, in predictive, supervised learning is when we have examples of input data and output data. So in the stock example, we would have previous history of the input, such as economic data and company performance measures, and then how that stock performed over the next couple of months. And we'd use that input and output data to make predictions on the future. In the descriptive type of learning, which is unsupervised learning, we only have the input data and we don't necessarily know what the output's going to look like. And so that differs there. There is a third, and reinforcement learning can sometimes fall under unsupervised learning, but it in general is called semi-unsupervised. But for now, just knowing these two types of learning is going to be more than enough. And we are going to actually devote the entirety of Unit 2 into supervised learning and the entirety of Unit 3 into unsupervised learning. So we will get a much better understanding of what these algorithms are doing in those units. In the second video in this series, we're also going to dive into supervised and unsupervised learning a little bit more and give you some specifics on the type of algorithms that encompass both types of learning. So again, and I mentioned reinforcement learning, that sometimes falls under semi-supervised learning. It's kind of a gray area. We don't necessarily have output data, but we're teaching it in much the same way we would a predictive algorithm. But we'll talk more about that later. So I also want to talk about machine learning as statistical learning. Sometimes these are differentiated, but it's really the same thing. Machine learning is based on the theory of statistics and is built on math because the core task is making inference from a sample. This is exactly what statistics tries to do when you get into things such as probability theory. So a machine learning algorithm is based on statistical properties. And as a result, it doesn't really understand necessarily what it's doing, but it's going to try to make approximations or generate an output based on statistical probabilities. So that's a core essential concept of machine learning that needs to be understood, that this is all based in statistics. As a result, when we get to video 4 and we talk about the core math competencies, statistics and probability theory is definitely going to be on that list. All right, and so here's a quick term comparison so that we can kind of understand where the overlaps are, because you'll hear both sides of these terms being thrown around, and it can kind of get confusing if we don't differentiate them early. So in machine learning, we have networks and graphs, or algorithms. You might hear a machine learning network or a machine learning algorithm. And this, in statistics, is simply a model. So it's something that we're trying to use to model a different scenario. And then we have parameters, which in machine learning are going to be called weights. So when we said machine learning is using a computer program to optimize a performance criterion, where we're optimizing those parameters, these are the weights that we're going to be adjusting in machine learning. And then that learning phase in statistics would be called like fitting, like curve fitting, and it's going to be used in much the same way. And here we have supervised learning, unsupervised learning. In statistics, these are formally called regression, classification for supervised learning. Classification being when you have a qualitative output, when regression when you have a quantitative output. So the difference is numerical or class. And then in unsupervised learning, we have things like density estimation and clustering algorithms. You might have heard of k-means clustering, and we'll talk a lot more about those specific clustering algorithms later. But for now, I want you to pay attention to the Google Research blog. Something that I want to do in all of these videos is provide you with a current article that highlights some cool things that are going on in machine learning today. So if you haven't checked out the Google Research blog, you should definitely do so. This is a great article on how a deep learning algorithm is being used to assist pathologists in detecting breast cancer. Very cool application of machine learning, worth the read. And again, if you haven't heard of Google Research blog, spend some time on there because they have a lot of good information on machine learning. Google has all of the data. As a result, they are one of the leaders in machine learning research. So it's always good to pay attention to what they are doing. All right, and so that concludes this first video. What is machine learning? I appreciate all you guys listening, and I look to have you guys back for video 2, where we'll talk about the types and applications of machine learning. Thanks for listening.
Hello everybody, welcome to the second video of Unit 1, an introduction to machine learning. This video is going to cover the types and applications of machine learning. This is presented by Etionics. So let's get started. We're going to talk about 3 types of learning. The first, supervised learning, in that classification and regression algorithms. We're going to talk about unsupervised learning and how that differs. And then finally, we're going to touch on reinforcement learning. And for all of these different types, we're going to give you some use case scenarios and some examples so that you can understand how and where these algorithms would be used. So let's get started. Again, this is the types and applications of machine learning. All right, so our first type, supervised learning. If you remember, we touched on this briefly in the first video. In supervised learning, you're going to have inputs and outputs, and you're going to have an algorithm that transforms your inputs to your outputs. For supervised learning, the inputs are often called predictors or the independent variable, where the outputs are going to be your responses or dependent variable. So in supervised learning, the machine learning program optimizes the parameters such that the approximation error is minimized. That is, our estimates are as close as possible to the correct values given in the training set. So we want to adjust g of x here in our algorithm so that we minimize our approximation error. So let's take a look at what that would look like. Example 1, we have email spam. And in this scenario, this was a real problem that was solved with machine learning. An automatic spam detector was developed that could filter out spam before clogging the user's mailbox. So to do this, they had a data set of 4,601 email messages, and they classified them into either email or spam. So the outcome class here is just two classes. It's either a genuine email or it's a spam email. And because our output is a class, this is, again, a classification problem. For this problem, not all errors are equal. We want to avoid filtering out good email while letting spam get through is not as desirable, but less serious in its consequences. And again, so this was solved with a classification algorithm and is an example of how a supervised learning algorithm might be used. And again, it's supervised learning, so we have both the inputs and outputs. We start with a database of email messages, which are our inputs, and they are labeled according to email or spam. And we can use that information to train the algorithm. Example 2, handwritten digit recognition. So in this example, we had zip codes that were written on envelopes from from the US Postal Service, and they wanted to automatically read these zip codes. However, if you might have noticed, myself included, a lot of people have very bad handwriting, and so sometimes these things are difficult to read. For this problem, you're going to have an output class, 10 output classes actually, 0 to 9. So if you notice, we can have more than 2 output classes. We can have any number of inputs and any number of outputs in these problems. And again, this is a classification problem. Even though it's technically a numerical output here, it's actually just a class because it's the 0 class, 1 class, 2 class, all the way up to 9. For this scenario, we had an input of a 16 by 16 matrix of pixel intensities ranging from 0 to 255 in an 8-bit grayscale image. So on the right here, you see each number. One of these little boxes would be considered the input. So it's a 16 by 16 matrix. That means you have 256 different inputs, where each input is just a pixel intensity at a given location. So this problem has many more output classes and way more inputs as well. So these networks can get pretty big pretty quick depending on the type of problem that you're working on. And again, this is a classification problem. So let's talk a little bit more about what classification algorithms entail. So in classification, you have your inputs, you have your algorithm, and then your output is going to be a class. A lot of these algorithms are going to be defined by the type of output that they produce. So classification, you have a qualitative output, and this is the defining feature of a classification algorithm. So let's look at an example, credit scoring. Not necessarily generating a credit score, but using that credit score to predict in advance whether a customer is going to be a high-risk or low-risk loaner. So the bank wants to use this to determine how good of a loan they can give you, and it's going to be based on the credit score and past information about the customer, such as demographics, maybe how much money they have in the savings account, their income, stuff like this. So multiple inputs, and your output is going to be a simple class, either high risk or low risk. So let's talk about the features that are going to go into this. First, you're trying to produce a discriminant, and a discriminant is simply a rule that's going to tell you whether or not you're a low risk or high risk customer. So the discriminant is simply a function that separates the examples of different classes. So in this scenario, it's pretty simple because we only have 2 output classes. And actually, to even further simplify the problem, we're going to pretend that we only have 2 inputs as well, being income and savings. So we could produce a general rule as such: if income is greater than this value and savings is greater than this second value, then low risk, else high risk. So we wouldn't necessarily need a machine learning algorithm to produce this specific discriminant. However, as soon as you generate more inputs and you have a higher number of output classes, these problems can become very complex, and a simple discriminant is not going to necessarily work, or it's not going to be obvious to you or me. And in those scenarios, we would use a machine learning algorithm to actually form that discriminant. And then once we have that discriminant, we can move on to prediction. So this is what we want to use the discriminant for. We have a rule that fits the past data, and now we can make correct prediction for novelties or new incoming data that we might have. So this is the bread and butter of the classification algorithm. It's using that discriminant that we formed through training to predict what class new data is going to fall into. And again, this example has been simplified to only include income and savings. And so in this scenario, you can see we have a pretty simple line that's going to separate our low-risk customers from our high-risk customers. Again, this is only in 2-dimensional input space. As soon as we have a higher number of inputs, this problem becomes infinitely more complex. And in that scenario, we would need to use a machine learning algorithm to solve it. Some scenarios, you might want to predict probability. So instead of just an output of high risk or low risk, you'd actually want to develop a probability that they would be a high risk. And so we're going to talk a little bit about this later when we get into probability theory. However, it can be designated as such, where the probability of Y, low risk or high risk, and X, given the customer's attributes, is going to be written as such. So probability notation is going to be important moving forward, and it's going to be necessary to have a basic understanding of probability theory, which we will touch on more in the fourth video, where we talk about the essential math competencies for machine learning. Another feature that you can use classification algorithms for is pattern recognition. So in this scenario, you have optical character recognition, face recognition, medical diagnosis, and speech recognition. This list goes on and on. However, this is a main use case for classification algorithms. So let's talk about optical character recognition. When you or I looks at the letter A, we can distinguish pretty easily that it is the letter A. However, we might not be able to describe exactly why we say it's a letter A. There's certain rules. We know what an A should look like. However, everybody's handwriting differs, and it's not always easy to tell. But using context clues, the words around it, how they've written letters in the past, we're usually able to deduce what the person writing the text means. However, that's harder to train a computer to do. However, once we're using a classification algorithm, we can extract features that the machine learning algorithm is going to use to solve these problems. So it's going to learn to recognize patterns. It's going to learn to recognize features of the letter A and the letter B, C, D, all the way on, and use those to make correct predictions on novelties, on new incoming input data when it's faced with new handwriting or new faces or new speech, something of that nature. Another use of classification algorithms is knowledge extraction. And this is learning a rule from data, and this rule here is really the discriminant that we talked about earlier. All of machine learning is really knowledge extraction. However, we're talking about the specific rule that is learned from the past data in this scenario. So as soon as you learn a rule, it allows you to explain the data in a much simpler way. For example, if you had 1,000 flips of a coin and approximately half of them were heads, approximately half of them were tails, it would be much simpler to simply say that 50% of the time you're going to get heads and 50% of the time you're going to get tails than it is to store all that data for the flips and the frequencies of occurrences for heads and tails. And so it's going to benefit the user to develop that discriminant which separates the probability of heads versus the probability of tails. In our example before, we're separating low risk and high risk customers. So this is going to tell us about the properties of low risk customers as well as the properties of high risk customers as well. So the discriminant here is the knowledge that we're extracting, and that can be accomplished using a classification algorithm. Once we have that rule extracted, we can use the classification algorithm for compression. And this is really what I was talking about as well with the flipping of the coin, because storing all of the data, all the heads and the tails and when they occurred, is going to be computationally intensive. It's going to require a lot of memory in our computer, especially when we're getting into larger data sets and stuff like that. However, if we fit a rule for the data, we can explain it simpler, and that is going to be easier to store on our computer. So as a result, classification algorithms can also be used for compression. Classification algorithms can also be used for outlier detection. Again, we have a rule, so now we can see scenarios that don't follow the rule and are really exceptions. And as a result, we can classify them as outliers. So as soon as our algorithm detects something that's not behaving according to the rule, we can classify it as an outlier. And as a result, classification algorithms are used fairly frequently to do outlier detection. And again, outlier detection is going to be based heavily in statistics. So we talked about probability theory. Again, one of those core math competencies is statistics, definitely. All right, now that we've talked about classification algorithms a little bit, let's switch over to regression algorithms. Whereas classification algorithms are designated by their qualitative output, regression algorithms are going to have a quantitative output. So you have your inputs, your algorithm, and what you're producing is going to be a number. So that is the designating feature of a regression algorithm. It's quantitative output. So let's take a look at how this would be used. It could be used for generating a used car price. So in this example, we would have the inputs of car attributes such as the brand, the year, the mileage, all these things. How many past owners, has it been in an accident? You could have any number of inputs. And the output is just going to be a numerical price. So you're not going to have any classes. Instead, one simple quantitative output based on any number of inputs. And so this is really function fitting. This is what this is called in statistics. You could have a function y equals mx plus b. This is, again, a very simple example and could become infinitely more complex depending on the number of inputs that you have. But the output, again, is just going to be a simple price, a numerical output y. And m and b in this scenario are going to be the parameters that we optimize. So in this example, the model is linear, and we have m and b are the parameters that are optimized for the best fit to the training data. In cases where the linear model is too restrictive, we could use, for example, a quadratic function or a higher order polynomial or any other nonlinear function of the input. This time optimizing its parameters for best fit. So we're really doing best fit here, and this can be shown in this simple example where we've only looked at the inputs price and mileage. So again, this is just a two-dimensional input space where we're really just doing a best fit line to explain the data. As soon as we generate more inputs, we have a high number of inputs, this becomes, again, infinitely more complex, and we can't model it in such simple terms. However, we can think about it as simply adjusting the slope and the y-intercept, m and b here, to best fit the data. As soon as we add more inputs, we're going to have to get a higher order polynomial to explain the data. So let's talk about unsupervised learning. This is a much different scenario than supervised learning and is actually kind of its counterpart, the second half of machine learning. Unsupervised learning is characterized by the lack of output data. We have no labeled responses. For these scenarios, we only have the input data to work with, and we don't necessarily know what we're looking for. However, we do have a goal. We're going to try to find regularities in the input. For unsupervised learning, we're making an assumption that there is a structure to the input space such that certain patterns occur more often than others. And we want to see what generally happens and what does not. So this is when we're trying to extract that knowledge from the data, not necessarily knowing what we're looking for. In statistics, this is called density estimation. We assume that the input space is structured. Again, as a result, certain patterns are going to occur more often than others. And we want to look for these patterns so that we can use them in different scenarios. And we'll talk about some of those scenarios later. In machine learning, this is called clustering. You might have heard of k-means clustering. Clustering comes up a lot and is the primary function of unsupervised learning. And it's really a method for density estimation. Again, we've talked about the different terms used in statistics versus machine learning. This is a scenario where machine learning's started to call density estimation clustering. And the aim is to find clusters or groups of the inputs that naturally separate towards each other. So let's take a look at this image. On the left, we have original unclustered data. And looking at this, you might not be able to make sharp distinctions between where the data occurs, but on the right, it's pretty obvious that we can separate this into 3 clusters of data. At least that's what it looks like when it's color-coded as such. We might be able to tell that there's a grouping of clusters in the bottom right and the left image, or a grouping of data points. On the right, it's pretty obvious that that is the red cluster, whereas the blue and the green can also be differentiated as well. So this is a clustering that would be done with machine learning algorithms. And again, this is just in two-dimensional input space. As soon as you have a higher number of inputs, clustering these data points is not conceptually easy when it doesn't fit into a 2- or 3-dimensional space. So let's talk about an example. We could use this to look at customer data, and it would provide the company with natural groupings of its customers. In the business world, this is called customer segmentation. So our customer data contains demographic info, and we're also going to have past transactions by all of those customers. And then we can use that information to decide strategies to target specific groups or tailor our advertising to those groups. For example, maybe Jack in the Box learns that they have a large group of customers who get the munchies late at night and come in past 10 o'clock. As a result, they're going to start targeting those groups of individuals. Whereas maybe a investment company or a retirement company learns they have a large demographic of retired individuals and they're going to target them. So we want to learn more about the natural groupings of customers so that we can use advertising and strategies to target them better. Another example would be document clustering. And this is where we're going to try to group similar documents. So a document would be represented as a bag of words in this scenario. We're probably going to remove non-informative words such as of, the, a, and focus on more of the nouns and verbs that would occur. And once we have that bag of words, that bag of words would be used as an n-dimensional input. It would be a vector whose element I is 1 if word I appears in the document or not. And then we can cluster these documents into similar types of documents. So a news company might use document clustering to sort news articles that relate to sports versus news articles that relate to travel or maybe politics. Each of those documents is going to have natural groupings. The words that occur in a political news piece are going to be much different than the words that occur in a sports piece. As a result, they can be separated using an unsupervised learning algorithm of this type. So that's unsupervised learning. Let's jump over to reinforcement learning. Reinforcement learning doesn't really fall into supervised or unsupervised learning. Sometimes it's called semi-supervised learning or Q learning. In reinforcement learning, we're going to have our observations, which are our inputs, our algorithm, and then as a result, we're going to have a sequence of actions. So the output here isn't a class, it isn't numerical, but it's going to be a combination of actions that allow us to reach our goal. So each individual action isn't going to be important, but the policy, the sequence of correct actions to reach the goal is going to be what is essential. So reinforcement learning algorithms have a lot of really interesting use cases. Example 1, game playing. Move is good if it's part of a good game playing policy. However, each individual move isn't as important. What's important is winning the game. Games are really easy to describe. They have a set of rules that can be defined. Thinking of chess, it's pretty easy to program the rules of chess, but it's much more difficult to actually play. So reinforcement learning and game playing specifically is very important to AI and machine learning. And some examples of this are with the games chess or Go. AI algorithms or machine learning algorithms, they're really reinforcement learning algorithms, have been used to master both chess and Go. And so I said I wanted to include articles about current advancements. This article is about a year old, but it's definitely worth a read. In this article, which appeared in Nature, an international weekly journal of science, which is very well regarded, the Google AI algorithm actually beat several professionals at the game of Go. The game of Go has more possible games than atoms in the observable universe. So for an algorithm to be able to play this game and play it effectively is very impressive. And this is very important research to machine learning and AI in general. And again, of course, it's Google who's doing this. Google has all of the data, and so they are definitely on the forefront of machine learning. Another example of reinforcement learning would be robot navigation. So a robot can move in one of any number of directions. How each individual move isn't as important as long as it meets its final goal. So it'll learn the correct sequence of actions to reach the goal state from the initial state, and reaching that goal state is what's important. We're certainly going to try to optimize our route to the goal state. We want to reach the goal state as efficiently as we possibly can. We don't want to have a self-driving car that's bouncing off the rails on the road as it drives down the street. We want to get there efficiently and safely. So we're going to try to optimize that route, but each individual move, again, isn't as important as making it to the goal state. So we're going to have a final project at the end of this class, and in this final project, we're going to take a look at the OpenAI Gym. So the OpenAI Gym is an environment that has been used to train reinforcement learning algorithms into play like Atari games or other similar tasks such as that. So the scenario we're going to look at is the cart pole, where we're actually balancing a pole on a cart. So this pole has a tendency to fall due to gravity. However, our reinforcement learning algorithm is going to learn to actually balance the pole on top of it. So this is a deep learning reinforcement algorithm, and we're going to talk more about deep learning and neural networks in Unit 4. We're going to talk about reinforcement learning more in depth in Unit 3 when we talk about unsupervised learning. So this will be a great program to take a look at so that we can understand these topics better. And this is going to be programmed in Python using TensorFlow, which is a machine learning package that was developed by Google again. And so this will be a really fun, challenging problem for us to do that will help reinforce some of these concepts that we're talking about in this class. Okay, so that concludes our second video, the types and applications of machine learning algorithms. Let's do a quick summary. We have supervised learning, where we have inputs and outputs. In supervised learning, we have classification algorithms, which have a qualitative output, and we also have regression algorithms which have a quantitative output. In unsupervised learning, we have no labeled data. We only have the input data, and we're looking for natural groupings or clusters of the data so that we can use that knowledge for different purposes like targeted advertising. And then finally, we have reinforcement learning, which is sometimes called semi-supervised learning, and we are trying to generate a sequence of actions to reach a goal state. So we have observations, we feed those into our algorithm, we get a sequence of actions out. Thanks for listening. Our next video is going to be on the differences between artificial intelligence and machine learning, as well as the similarities, where there's overlap and where there's misunderstandings. Thanks for listening. Hello and welcome back. This is the third video of Unit 1, an introduction to machine learning. This video is going to cover artificial intelligence versus machine learning. What are the differences? Where are there similarities? Hopefully those questions will be able to be answered by the end of this video. So let's get started. What is the difference? How is artificial intelligence even defined? And we can start by that here. This is the definition that Google provides. Artificial intelligence is simply the theory and development of computer systems that are able to perform tasks that normally require human intelligence. So these tasks include things such as visual perception, speech recognition, decision-making, translation. All of these tasks are normally performed by humans, but notice that the definition does not require a means of accomplishing those tasks. So regardless of how we do visual perception, or regardless of how we do speech recognition, we're still going to be using artificial intelligence as long as it's done on a computer system. So let's contrast that a little bit with machine learning. And machine learning can be really defined as a subset of artificial intelligence because it's often used to accomplish tasks like speech recognition. This is a computer program that can be used to do AI tasks. In 1959, Arthur Samuel was really credited with the idea for machine learning. He decided that we could teach computers how to learn instead of trying to give them a large rule set or teach them every single little thing that they would need to know about the world. So this is more similar to how you and I think, and really began the route towards machine learning. However, it wasn't necessarily possible until we developed the internet and we started collecting all of this data. So the data is really the essential part of machine learning because we have to learn from past experience. So until we had good data sets developed, we couldn't do much machine learning. However, now that we have that, we're able to accomplish some of the tasks that were noted in our AI definition in the first slide. However, what machine learning is not is probably a better way to understand the differences between artificial intelligence and machine learning. First, machine learning is not logic. It is not rule satisfaction. So for example, if we had a simple logic scenario like if A meets B and B knows C, does A know C? This is a question that machine learning would not be able to answer. Again, remember, machine learning is based in statistics. It's not necessarily based in logic. So when it comes to logic and rule satisfaction, we have to rule machine learning out. Machine learning is not artificial intelligence in the sense that it has an understanding of the world. And we'll give you some more examples of why machine learning doesn't understand in a second. But when we picture artificial intelligence, we're typically thinking about something like Sunny from iRobot. If you've seen iRobot, Sunny is a robot who starts to display emotions like anger or love. Artificial intelligence right now isn't able to do that because machine learning doesn't display understandings or emotions in this way. Finally, machine learning is not biology and neuroscience. We do have neural networks which are inspired by biology. However, they have no requirement to function in the same way that our brain does. For example, we built fighter jets and they work great. However, fighter jets don't flap their wings like a bird does. Sometimes the best methods are not always the ones that are biologically inspired or similar to our own minds. So we have plenty of machine learning networks that aren't similar to what you might find in the brains of you or I. However, some of the networks are, and that is neural networks and deep learning specifically. Those will be covered more thoroughly in Unit 4 when we talk about neural networks. Convolutional neural networks are a really cool aspect of machine learning that are starting to be used for a lot of tasks. So we'll talk about that later, but it's important to know that machine learning is not a study of neuroscience or a study of biology. So here's an example of why a machine learning algorithm does not understand. And that example is adversarial imagery. So this would be a deep neural network, and it's being used for an image classification task. So on the left here, we have a panda, which is classifying with fairly good confidence. However, if we perturb the pixel intensities by a very slight amount, in this case 0.007%, of what seems like a random direction, we are going to trick the machine learning algorithm to classifying this image as something entirely different. In this case, a given, it thinks it's a monkey on the right with 99.3% confidence. If you look at the image on the left and the image on the right, you and I could not tell the difference between these two images. However, the machine learning network is entirely fooled. And that's because we've changed the image ever so slightly in the most significant direction possible. You notice the gradient below the middle image and the right image. We're moving in the direction of the most damaging direction, and we're very easily able to trick the machine learning network. You and I can understand that these images are the same. These are both pandas. However, because of the way machine learning networks work, it doesn't understand that there's not a significant difference between these images. And there's plenty of examples of adversarial imagery and other adversarial examples out there on the internet. I would encourage you to research them further if you wanted to understand more about what a machine learning network can understand. Okay, so let's move on. We also talked about rule satisfaction. A rule-based AI system has been around for a while. Here is an example, Eliza, and you can see this interaction where the rule-based AI is trying to fill the role of a psychotherapist. However, the user quickly becomes frustrated simply because the answers and the questions that this AI is asking don't necessarily make sense. You may have noticed this when you're interacting with a chatbot online or something of that nature. Rule-based AI systems don't always work. And this is not machine learning. This is an example of an artificial intelligence that doesn't use machine learning. Granted, this was in 1970. We have much better systems out there today. However, this is just a good example to show that artificial intelligence doesn't always have to be machine learning. We can accomplish tasks like speech recognition without using machine learning in a lot of different scenarios. Visual perception doesn't always have to be machine learning based. We can do static image processing and actually solve many computer vision tasks more effectively than using deep learning methods, simply using thresholding techniques or contour detection, something like that. So artificial intelligence doesn't have to be machine learning. However, in many scenarios, it does use it. Machine learning can be considered the new cutting edge of artificial intelligence research. So visual perception tasks, we are starting to develop deep learning networks that are really good at visual perception. Natural language processing would be another example of a scenario where we're using machine learning algorithms to form an artificial intelligence role, and we're doing it quite well. So with the advent of deep learning, we've really increased the complexity and the advent of the neural network. These two things have improved artificial intelligence research significantly. So while AI doesn't have to be machine learning, it can use machine learning in a lot of scenarios to accomplish the task that it is trying to do. So that's just a quick summary on artificial intelligence and machine learning. I mentioned that this would be a short video. If you'd like to learn more about the differences, we can go into that in more detail in the future units, such as Unit 4, when we're talking about deep learning and neural networks specifically. When we think about machine learning and artificial intelligence, it's often that neural network that people are imagining. In our next video, we're going to talk about the core math competencies for machine learning and artificial intelligence research.
Hello everybody, welcome to the fourth and final video in Unit 1, an introduction to machine learning. This video is going to discuss the essential math competencies to machine learning and artificial intelligence research. Going in, it's essential that we have a mathematical background so that we can understand how and why algorithms are structured the way they are. So let's dive right in. The first thing we're going to talk about is multivariate calculus. Calculus is the best math we have to talk about smooth changes. And when it comes to machine learning, this is happening constantly. When we have optimization problems, what we're really trying to do is minimize the error. And we do this by using derivatives and gradients. When we're doing probability measurements, we're going to do integrations to sum up the weights and get our probabilities. So we're using both derivatives and integration in a variety of different settings. But let's go ahead and dive in and see some of those actual examples. So the first would be our optimization via gradient descent. Gradient descent is actually how we train all of these models to optimize their parameters. So here we minimize the objective function, whatever the objective function may be. Typically it's going to be your error. So we're trying to minimize error here, if that would be our objective function, over our model's parameters. Eta here, the Greek symbol, is going to be the learning rate, and it's going to determine the step size of our actual gradient descent. So when we start getting into the parameters that these functions use, such as learning rate, understanding the math behind the algorithms is going to help you optimize the different settings in the most appropriate way. So when you're adjusting learning rate, it helps to understand gradient descent so that you can adjust that value appropriately. And this is essentially just trying to find a local minimum using our error equation to the left. Again, we have the gradient, and the gradient is built up of derivatives, so it's important to know multivariate calculus so that we can do this math. Furthermore, this problem becomes much more difficult when you have a high number of inputs, and theta here, our parameters, are many, because then you're working over high dimensions as well, and it's harder to visualize this conceptually. So you have to have a good background in the math so that you can understand how to do optimization problems. We're also going to use integration to find probability calculations. So in most of these problems, we're going to get probability density functions, and this is essentially just a distribution of the probabilities, and we can find the total probability by integrating over a certain range. Integrating over the entire range is going to give us 100% or 100% chance of that happening. Integrating over a particular range is going to give us a smaller probability. So it's important to know integrals because these probability density functions are often going to be solved via integration. So let's talk about another example of that, and this is in Bayesian inference. So this is a statistical inference in which Bayes' theorem, which we're going to talk about, is used to update the probability for a hypothesis as more evidence or information becomes available. So let's go over this. We have a data set, and we can use Bayes' rule, which we will go into in a later slide in more detail. However, what Bayes' rule often gives you is a posterior distribution, and solving this distribution is known as the inference problem. And as you can see, we have an integration over d theta, and theta here is going to be our parameters. So when you have many parameters, this isn't just a single integral. It can be a double, triple, all the way up to however many parameters we have. And solving this integral can get very difficult because of its high dimensional nature. So Bayesian inference is something that you should understand as well, and solving the integrations on the posterior distribution is going to be one of the main reasons that you need to know multivariate calculus. But this is actually a good segue into the topic that we're going to talk about next, and that is probability theory. So statistics and probability theory is absolutely essential for machine learning and artificial intelligence. We need statistics to deal with uncertain events. That's what we're trying to do in almost every scenario in machine learning. We also need statistics to develop mathematical formulations for probabilities. We saw our posterior distribution in the previous slide. This is going to be a mathematical formulation for probability, and so solving that is going to be based in statistics. We also needed to estimate probabilities from data. All of this, again, is based in statistics and probability theory. But we can probably understand this better if we actually dive into an example. And so we're going to come back with Bayes' rule, and this is really modeling dependence and conditional probability. So this is the assumption that knowing X will tell us something about Y. Or perhaps we could say knowing something about previous data will tell us something about the future. Again, this is what machine learning is based around. So in this scenario, we have the probability of Y given X times the probability of X is going to be equal to the probability of Y and X. And again, that is equal to the probability of X given Y times the probability of Y. And solving that, moving some things around algebraically, is going to give us Bayes' rule. That is, the probability of X given that we know Y is going to be equal to the probability of Y given X times the probability of X divided by the probability of Y. So that's a lot of words and letters and variables that is explained better through an actual example. So let's use that. We're going to do an AIDS test. How likely is it to have AIDS if you test positive? It seems pretty likely, doesn't it, if you're testing positive? But let's actually see. So we're going to start with a couple assumptions here. Roughly 0.1% of the population is infected with AIDS. So we have the probability of X equals AIDS is equal to 0.001. This is 0.1%. Our next assumption, the test reports positive for all infections. If you have an infection, 100% of the time you are going to be testing positive. So we have the probability of y test positive given that x, you have AIDS, is equal to 1. Our next assumption, the AIDS test reports positive for 1% of healthy people. So we have some false positives here in this test. 1% of the time it's going to say you have AIDS when you actually don't. So the probability of y test positive given that you are healthy is equal to 0.01. So let's plug this into Bayes' rule to find the probability of AIDS given that you test positive. This is the probability of x given that y, you're testing positive on this test. So here's the formula again for Bayes' rule, probability of x given that y, and plugging in our actual, or solving first, and then we can plug in our actual numbers. We have the probability of y given x and the probability of x. Those are from above. This x over capital X on the bottom here is just going to be the inverse. So instead of 0.01 or 0.001, we have 0.999. And so this is going to spit out 0.091. There's actually only a 9.1% chance that if you test positive, you actually have AIDS. So Bayes' rule is telling us something here that is probably counterintuitive. And this is why having a strong understanding of probability theory and statistics is essential for machine learning, because oftentimes the outputs and probabilities are going to be counterintuitive. So it's essential to understand that going in. However, let's continue on this example and improve our inference by following up with an additional test. So what we're going to do is perform a follow-up with an independent test. It's independent to the first one, which has the following properties. Second test reports positive for 90% of the infections. So if you have an infection, 90% of the time it's going to catch it. The second test reports positive for 5% of healthy people. So we have a slightly higher false positive rate here for this second test. Here we're going to add this into our formulation of Bayes' rule in the previous slide, and we simply have the additions of the 0.05 highlighted in red here and the 0.9 into our formula that we had written out before. And all of a sudden, our chances of actually having AIDS go up to 35.7% from 9%. So it's increased significantly by having an additional data point. So what we can conclude, adding extra observations can improve the confidence of the test considerably. So extra observations in machine learning are going to be additional tests or data points. And this is why having large data sets is essential to developing good algorithms in machine learning. Each additional data point that you have improves your inference significantly. And when we're inferring knowledge from data, this is everything. So let's do a quick mini summary. Probability theory is used to model uncertain events. Dependence and independence is what we end up exploiting for estimation, which leads us to Bayes' rule. And finally, prior probability matters, the prior probability of AIDS in our example. And then combining tests improves outcomes significantly. But let's move on. Our last core math competency is going to be linear algebra. And this is a branch of mathematics that lets you concisely describe coordinates and interactions of planes in higher dimensions and perform operations on them. We were mentioning in previous videos, as soon as we add additional inputs, we're getting into a higher dimension. If we have 2 inputs, that's 2 dimensions, 3 inputs, 3 dimensions, 4, 5, etc. Some of these algorithms are going to have hundreds, if not thousands, of inputs. When we're thinking about an image, even a 16 by 16 matrix 8-bit image is going to have 256 different inputs. So doing math in 256 dimensions is going to be impossible without an understanding of linear algebra. So why linear algebra? First, it's a foundation field. So a lot of the calculus and the probability theory is going to use linear algebra, if not just linear algebra notation, in its formulations. Also, matrices and vectors are how these algorithms are represented. Our inputs are going to be matrices or vectors, and our outputs are also often going to be matrices or vectors as well. And again, we have high dimensional representations of the data. When we are working in higher dimensional space, it's important to use linear algebra to solve and perform the operations that we need to on the data. So we're solving in high dimensions, and we're using the linear algebra to perform those operations. And again, we have the notation. This notation is used almost exclusively in machine learning, as well as in many other areas, so it's just good to know because so many other maths are based on it. So here, this is just matrices and vectors. We have scalars, vectors, and matrices. If this doesn't look incredibly familiar to you, I would highly encourage doing a quick crash course on linear algebra before getting started. So a scalar, we just have one numerical value, while a vector, we're going to have a row vector or a column vector, which is going to be a set of those scalars. And then a matrix is expanding that to 2 dimensions. Here you have a row times column. The indexing in matrices is going to be incredibly important. Again, this is just a 2-dimensional matrix. We're going to get up into high dimensional structures where the math becomes unintuitive. So understanding linear algebra and how it relates to the other core math competencies like probability theory and multivariate calculus is going to be essential going in. So here's the minimum linear algebra that you should know for machine learning. 1, the most essential is notation. Understanding the algorithm structure as well as the input and output structure is going to be impossible if you're not at least familiar with the notation used in linear algebra. How does indexing for a matrix work, for example, is going to be something that you need to know in order to understand how to feed data into these algorithms. Notation is going to be essential even if you're not trying to develop your own algorithms. Even just applying an algorithm that somebody else has built, you're going to need to know notation. It's also going to be incredibly helpful to know linear algebra operations. When we're working at the next level of abstraction in the vectors and matrices, learning to apply simple operations like adding, multiplying, inverting, transposing, etc. on these matrices and vectors is going to be necessary. So these operations are used a lot, and so understanding them before going in is going to help you apply and use these algorithms efficiently. So here we have a quick summary. The 3 keys. 1, multivariate calculus. You got to know calculus because we're working with smoothing problems, optimization problems using gradient descent and error minimization, and we're also doing summations and integrations when we're solving for our probabilities. You have to know probability theory because, again, machine learning is based in statistics. So understanding statistics and probability theory is going to help you understand the why and the how these algorithms are working. And finally, linear algebra is necessary because most of our inputs and outputs and the actual algorithm structure itself is going to use linear algebra notations and use linear algebra operations. When we're working in high dimensional spaces, the only way to do this is via linear algebra. If you want to learn more, you can check out some of these recommended resources. 2 great books that are available online. You have The Information Theory, Inference and Learning Algorithms by David McKay. That one goes over a lot of the probability theory that is going to be important to this machine learning research, as well as The Elements of Statistical Learning by these 3 authors. It's an incredible book that goes into a lot of the stuff that we're going to cover in this class, but also dives into the math behind it so that you can understand why these algorithms are working the way they do. All right, everybody, thank you for listening to this 4th and final video, the Essential Math Competencies. This is going to include Unit 1, our Introduction to Machine Learning. So you should have a basis now to understand what is machine learning, the types of machine learning that are out there, and in Unit 2 and 3, we're going to dive into the specifics. So Unit 2 is going to cover supervised learning, so we're going to learn a lot more about classification and regression algorithms, the math behind them and how they work and where they should be used. In Unit 3, again, we're going to dive into the unsupervised learning, and this is going to cover clustering, how that works, as well as have a section on reinforcement learning, since it kind of falls under that unsupervised category. Thanks again for listening and following along.